going to get this camera set up first.
ดูรักไข่ดาวเอาไข่ดาว
So it's been a few weeks since Mary's talk, so I'm just going to start with what a functional is. So if we remember, functions take in a real number.
Oh, put the audio on.
Can you actually hear me? Okay. Yeah. So we have functions which take in a real number or a vector, and they output a real number. So this is what we've done in first year calculus courses, and then we have this new thing here called a functional. So a functional takes in a function and outputs a number. And today we're going to be considering a functional which is the form, takes the form of a definite integral. So J is our functional here, and it's going to be integral from x0 to x1 of this integrand, with which takes x, y, and the first derivative of y as its parameters. Later Maggie will generalize this, but currently this is what we're focusing on. And an example of a functional problem, because the calculus of variations is concerned usually with optimization problems and finding the maximum and minimum points of minimum functions for these functionals. Just as an example, consider 2 points in a plane. So x0, y0, and x1, y1. And the question is, what is the shortest path between the 2 points in plane? So if we consider an arbitrary function y, so it might go like this, then we know that the arc length formula is given by this integral here, and J here is a functional, and this integrand here is f, x, y, y dash. So the idea of functionals is we can plug in any function y here, and we'll get back a value for our integral. But before we focus on how to find maxima and minima for functionals, we're just going to go to functions so that we can build up some intuition first. So let's say we have a function here, and we have a maximum at x. So this is f of x, and we have a maximum. And now we want to consider a quantity x hat that is near x. So specifically we want x hat which is no further than some number epsilon away from x, where epsilon is greater than 0. So we have an interval x minus epsilon, x plus epsilon, and x hat lies on this interval. And here's f of x hat. And what you might notice is that if x is a maximum point, then this quantity f of x hat minus f of x is always going to be less than or equal to 0 for if x is maximum. Of course, if x is a minimum, then the sign is going to be the other way around. And the idea to get from this is that if x is an extremum, so a maximum or a minimum, then the quantity f of x hat minus f of x does not change sign for any x hat on this interval here. So now we have an idea of what an extremum is, but the question is, how do we actually find these extrema? And we know for functions of one variable here, we have if x is an extremum, then we have the derivative of x is equal to 0. There's many ways to prove this, but we'll prove it using Taylor series because this will come in useful when we move to functionals later. So proof, we know this expansion for Taylor series, only considering up to second term, and then I'm putting ellipsis afterwards. And then let's let x hat equal x plus epsilon beta. So epsilon eta represents a small change from x, in this case it will be this quantity here. Now the reason why we want epsilon and eta in this expression is because later eta is going to be a function, so we're building intuition here, so that will make more sense in the later case. And you can see that the absolute value of eta is going to be less than or equal to 1 here, since epsilon eta is going to be between eta and minus eta. If we replace x with x hat and a with x, then we get f of x hat equals f of x. X is being our minimum point here. We had the Taylor series about x equals a earlier. Now we're doing it about our minimum point. Unfortunately, there's a bit of notation clash here, but hopefully this will make a bit more sense in a moment. F dash x. This will be x hat minus x, which will be epsilon eta. And epsilon squared, eta squared, and so on. And now if we bring the fx to the other side, and factorize out epsilon, then we get this expression here. Now remember, this part here, f of x hat minus f of x, is what we don't want to have the sign change for any x hat on this interval. And the sign on the right-hand side is determined mainly by this linear term here, because epsilon, the epsilon out the front is not going to change the sign of the right-hand side. And for small enough epsilon, everything on the right here is going to be negligible. Even though there's a power of eta, the absolute value of eta is less than or equal to 1, and it's not going to contribute much to this term. So what this means is that f dash x, f dash x eta does not change sign for x for any x hat on the interval. And what we can notice about eta is that if x hat is on the right hand side of x, then eta is going to be positive. On the other hand, if x hat is on the left hand side of x, then eta is going to be negative. But we want f dash x eta to not change sign for any x hat, and hence for any eta. So we must have that f dash x equals 0. So are there any questions about this one? Okay, so I'm just going to keep this up here, and we can move on to functional now. So what we want to work with is, let's say we have a functional j, and j has the domain is c squared x0 x1 to the reals. And what this c squared x0 x1 means is that this is a set of functions with continuous second derivatives. Can everyone see this? Okay. And the x0 x1 here means that the functions themselves have a domain of x0 and x1. In general, if you have a function in the set ck of x, then this means that the function is k times continuously differentiable, and the function has domain x. So in this case, k equals 2, so we want continuous second derivatives. And we're considering something called a fixed endpoint variational problem, and it's for the one-dimensional case. So we'll have the functional we had earlier, which is j of y equals the integral of x0, x1 of a function of x, y, and the first derivative of y. So that's the functional we're considering right now. Now there's a few assumptions we need to make, which will come in useful later on, so I'll just write them up now. We need to assume that f has continuous partial derivatives, second order partial derivatives with respect to x, y, and y hat. And the other assumption we need to make is that we need to assume, since this is a fixed endpoint variation problem, we need to assume that y has fixed endpoints. So assume that we have fixed endpoints, say x0, y0, and x1, y1, or y. These assumptions will come in later, but we don't need to worry about them yet. And then applying this idea here, that if x is an extremum, f of x hat minus f of x does not change sign for any x hat, we can draw a similar parallel for j by having, I might change markers here. If y is an extremum for j, so either y maximizes or minimizes the value of this functional, then we have j of y hat minus j of y does not change sign for any y hat which is within a distance of epsilon away from y. So the way you write that is the norm of y hat minus y is less than epsilon. Now this norm symbol is similar to the one used for vectors, except here we're dealing with functions, so we have to think about how we define the distance between two functions. And the way, there's many ways we can do this, and I'll give one example. And this is called the supremum norm. And the idea is you take the maximum difference in function value. So for example, if you have a function y hat here, and you have, say, y here, then the maximum difference in function values might be given by, say, this distance here, and this would be the distance between the functions. And what this condition, the normal y hat minus y less than epsilon means in our case, is we want to consider, let's say we have our fixed endpoints, x0, y0, and x1, y1, and this is our function y. We want to consider a strip of width epsilon above and below y. So if this is epsilon, this is epsilon, and above and below, and this is our strip, then what the condition, the normal y hat minus y less than epsilon would mean is that y hat has function values which lie completely inside the strip. So for example, y hat could be, sorry, that's my phone actually. Yeah, so y hat lies completely inside this strip here. And you can think as epsilon approaches 0, then the strip is going to get narrower and narrower, and y hat will approach our minimum or maximum y. And also, like our one variable case, remember we had to let x hat equal x plus epsilon eta here. If we go back to our functional case, then we let y hat equal y plus epsilon eta. Except the thing here now is these ones are all functions. So what we really have is y hat of x equals y of x plus epsilon eta of x. And since we're considering fixed endpoints, y hat and y have to have the same endpoints. And so eta of x0 is going to equal eta of x1, and that is going to be equal to 0, because we have no variation of y at the endpoints. Now, remember, we want to consider what happens when j of y hat minus j of y does not change sign. And substituting j of y hat minus j of y into the into the functional equation gives f of x y of hat dash and minus just j of y. Now to simplify this expression here, we have to use a Taylor series expansion for this term. And the expansion goes like this if I write it out. Because we're substituting y hat equals y plus epsilon eta. And the derivative of y hat is going to be y dash plus epsilon eta dash. And this expands to we have O of epsilon squared here. Some of you might have seen this notation before. It means that every term after is on the order of epsilon squared. So you can think of that as every term afterwards can have epsilon squared factored out of it. So we have something times epsilon squared plus something times epsilon cubed and so on after this right hand side here. And you'll notice that right here we don't have any x term. And that is because we're not considering a change in x. X stays constant in this expression. Does anyone have any questions about this expansion? Or very comfortable? It might be good to actually explain where this might come from. If we fix x and eta, then we can consider this function as a function of epsilon only. And if we do that, the Taylor series expansion for a function of one variable is about epsilon equals 0 is going to be g of 0 plus epsilon g prime 0 plus epsilon squared on 2 factorial g prime 0 and so on. Now you can notice g of 0 is just going to be f of x, y, f, y prime. Now this expression here is actually g dash 0 with the derivative taken with respect to epsilon. So if you try to evaluate this, and you will need to use the chain rule in order to do this, evaluated at epsilon equals 0, then you'll get this expression. And if we substitute this Taylor expansion into j of y hat minus j of y, the f of x, y, and y prime are going to cancel out. And what we are going to end up with is epsilon of the integral x0, x1, eta partial f partial y, and eta prime partial f partial y dash dx. And then everything afterwards is going to be on the order of epsilon squared. Everything else has an epsilon squared in the determinant. Now, this portion in here, this quantity, is what we call the first variation. And we represent this by a delta j of eta and y. Now you can think of this first variation as a sort of first derivative, because if you take epsilon to the other side by dividing, and take the limit as epsilon approaches 0, then what you will end up with is limit of epsilon equals 0, j of y hat minus j of y on epsilon. If you divide by epsilon and take the limit as epsilon goes to 0, every term here still has an epsilon in it. So on the right hand side here, all terms will tend to 0. And what you're left with is just the first variation. And of course, this here is actually a derivative taken with respect to epsilon. So the first variation is equal to the derivative of j of y hat with respect to epsilon evaluated at epsilon equals 0. So that's to gain some intuition about the first variation being a sort of first derivative. And this expression here is a sort of checkpoint, so I'll write this on the board. If y is an extrema, now we have the first variation this expression equaling 0. But unfortunately, as much as this is a first derivative of sorts, it's not very good at actually finding extrema for us because we have an eta term in here, and we can't actually do that do anything with that since eta is variable. So what we can do, however, is eliminate this eta prime term here using integration by parts. So if we do that, so the eta prime term is integral of eta prime partial f over partial y dash dx, as you can see over on the right here. And this is going to evaluate by taking v dash equals eta dash and taking u being this partial derivative here. It's going to be this. But remember, we had eta here having fixed endpoints. We had eta being 0 at the endpoints because y and y hat have the same endpoints. So what this means is that this expression is actually 0, and we're left with whatever is on the right-hand side here. And by substituting this into our first variation expression here, we get the integral of x0 x1, factorizing out eta, partial f over partial y minus d on dx, partial f over partial y prime. This expression equals 0. So I'll also write this on the board here. Now, if we let this be e of x, then we have the integral of a product of two functions equaling 0. So now we have something called the fundamental lemma of the calculus of variations, and the claim is because eta is variable, and since the product of eta e of x, the integral of that is equal to 0 for any choice of eta, the claim is that e of x is going to be 0 on this interval x0 to x1. So I'm not going to actually state what the lemma is fully, but this is an adapted version of it for this proof. So let's do a bit of a recap of what we have. Since y hat and y are in this c squared x0 x1 domain, eta itself is also in this domain. And we have the endpoint of eta being 0. Now this is where we need our conditions here. Assume that f has continuous second order partial derivatives with respect to x, y, and y prime. And this condition, what this does, it means that if you look over here, we've only got second order derivatives at most. If you expand this term out, you'll get partial derivatives, but at most they'll be second order. So what this means is that e of x is going to be continuous. And we have that for every choice of eta, we have this integral equaling 0. Now to give a sketch of how this proof works, let's consider the opposite. Let's say that the integral, we claim that e of x equals 0, and let's consider the opposite. So there is some point c where e of c is not 0, and without loss of generality, let's assume that it's positive. Now because e of x is continuous, then there exists some small interval, I'll just call that alpha beta, where e of x is still positive. and this is all between x0 and x1. Now, since we can pick out eta, and eta has endpoints of 0 at x0 and x1, why don't we pick eta to be 0 from x0 to alpha, 0 from beta to x1, and positive on the interior of this interval alpha beta. Now, the question of whether we can actually pick an eta satisfying this condition exists is not actually a problem. We can always find one. But what this does is that the integral is going to be positive now, because we have the product of two functions which are necessarily positive on this interval. And because the integral is positive now and non-zero, this is a contradiction, and hence we have e of x equals 0 on the interval x0 to x1. So are there any questions about this? If e of x equals 0, if e of x equals this, then we have this equation here. And this is the final step in our proof. This equation here is called the Euler-Lagrange equation. And if you follow this through, if y is an extrema, j of y hat minus j of y does not change sign for y hat within a no further away than epsilon away from y. Here, sorry, wrong color. Here we used Taylor series to get that the first variation is equal to 0. And then this here is integration by parts. And then finally, we use the fundamental lemma and we get this equation. So what this means is if y is an extremum for the function of j, then this equation is going to be satisfied. And so this is the Euler-Lagrange equation. If there's anything to take away from this, it's the idea that if y is an extremum for j, then this equation is satisfied. So in the time I have left, if you may recall that cos squared x minus 1 equals sine squared x. By the same token, on the bottom here, we've got c1 sine squared u. Sorry, c1 sine u, we'll have to take in square root. And on the top, we also have the same thing. So this simplifies to the integral of du. So what we have here is plus minus 1 on c1. Integral dx is just going to be x plus a constant equals u, and this equals to inverse cosh of y on c1 from here. And hence we get that the shape of a hanging chain, under perfect conditions of course, because that's how mathematics always works, is a cosh curve. So if you've never seen this problem before and you thought it was a parabola, then you'd be pretty close. Because if you remember, we have cosh x equal 1 plus x squared plus, and so on. So the Taylor series term cutting off at x squared is actually just parabola. So it's close, but not quite. We have a Koch curve. And that is it.